Hello and welcome. I am Dr. Anil Joshi. Welcomes you to my series Learn Radiology with Dr. Anil Joshi. Today's topic is MRI physics, that also a case space. Small name but big importance. Very important as far as MRI signals are concerned. We are going to see in brief today what is the meaning of case space and what is its role in MRI physics or MRI signal production. To start with are the disclosure, acknowledgement and disclaimers. This is the educational series and meant for medical professional interested in learning basics and also medical imaging technology students. All the material which we have used in this is from our department. However, some part of it is downloaded from net. However, we have confirmed that they are royalty free. Still, we acknowledge them with thanks because they have allowed us to use this material for educational purpose. And this website, this lecture series is totally a non-commercial educational series. With that brief, let's get going to the topic itself. Today's topic is case space. Case space is an array of numbers representing spatial frequencies in MRI image. So that is the definition. Although the K-space galaxy and MR images appear quite different, they contain identical information about the scanned objects. The two representations may be converted to one another using an advanced mathematical procedure that is called as Fourier Transformation. There is a different lecture covering this Fourier transformation in detail. Do visit our YouTube channel for this. This case space is the raw data for magnetic resonance imaging. The data acquired by the scanner are assembled and arranged internally into individual case space array. Each individual image is derived from a case space matrix. For example, for one slice image at 20 cardiac phases, there are 20 corresponding case space arrays. In most imaging modalities, the correlation between the physical properties sampled and the manner in which data are arranged to form an image is generally intuitively obvious. So you can imagine it and you will be correct in that way. In MRI, case space is acquired and the images are generated in a manner that is not naturally intuitive. However, case space is a feature that may have advantages over the other modalities. Case space breaks the one-to-one correspondence between the positions of the receiver and the orientation of the images. It allows arbitrarily sliced angulations. Case space allows reduction in scan time by post-processing the images. It allows parallel imaging which also reduces the scan time, and it allows imaging contrast to be altered. So that is required in our DICOM image viewings. Now how it supersedes the USG technique? In sonography, let's compare two techniques, sonography and MRI, as far as only pertaining to case space applications are concerned. What happens in sonography? Image is oriented directly proportional to the position of the probe. You change the probe, the image will change, its orientation will change. In any axis you can image an organ in MRI depending on your probe position. Now, therefore, the advantage is it is operator dependent, obviously, because we can get information in all the axes, and disadvantage is it has a limited imaging window. A small data is always imaged at same time. Therefore, it is contradicting and superior to ultrasound technique. It is contradicting, okay. However, still it is superior also. because we can analyze a larger data, we can at a time take a large volume of observations, and that is possible only because of the case space. Understanding of the case space is essentially understanding of MRI, because it will explain the advantages over other modalities. Mathematically, case space can be completely described by a single equation which will fulfill and explain what is case space. However, for a non-mathematics people like us, it can be just a series of meaningless symbols. So for a mathematician, it's a good understanding. As far as for non-mathematical people like us, it is a just series of meaningless symbols. Here we will discuss and explore case space by means of series of illustrations. So what is preferred? Let's see illustrations and discuss with the help of illustration and try to understand case space. Physically, case space is a matrix of data with dimensions that are typically square, and typically these are in a power of 2, like 128 by 128, 256 by 256, 512 by 512. The highest concentration of the signal is located towards the case space center. To generate an image, the case space data are Fourier transform. Sometimes this operation is referred to as a fast Fourier transformation. Now, what is a Fourier transformation? There is a separate lecture covered on this topic. Do visit it so that you can understand this concept in better ways, or if you already know it, fine, there is no difficulty in understanding it. This is due to a mathematical shortcut that was discovered for matrix with dimensions of power of 2. The image generated by the mathematical operation has a physical size identical to that of the original case space matrix, like 122 by 122, 256 by 256, and 512 by 512. In this respect, there is one-to-one correspondence between the number of case space points and the number of image points. Also note that the image features fit within the squares or rectangular field termed as field of vision, FOV, what we short form usually use. That is a field of vision, FOV. Once the case space data have been collected, discrete Fourier transformation is applied to the mathematically transform the data to image domain. So from one domain, the other is transferred to another domain. From the data, it is transferred now to image. The Fourier transformation takes the complex multi-frequency data and reports back with frequencies are present in data. So whichever frequencies constituent the data, by separation of them, Fourier transformation takes place. The result is the matrix of number that correspond to the image. So the signals here are changed from one domain to another domain. The unit of image are the inverse of the case space data, which mathematics with the idea that the image is map of frequencies generated using phase and frequencies encoding as previously described. The common pictorial representation of case space is a galaxy, what we can observe in the sky, which perpetuates the mystery. Now each star in case space is just a data point derived directly from the MR signals. The brightening of each star represents the relative contribution of that star's unique spatial frequency to the final image. We are just comparing two to have better understanding of case space signals. The cell of case space are commonly displayed on the rectangular grid with a principal axis like Kx and Ky. The Kx and Ky axis of case space correspond to the horizontal x and vertical x axis of the image. The k-axis, however, represents spatial frequencies in x and y directions rather than positions. Now, the individual point kx and ky in a k space do not correspond to one with individual pixel, that is x and y in the images. Each k space point contains spatial frequency and a phase information about every pixel in the final image. Conversely, each pixel in the image maps to every point in k space. The k space representation of the MR image is therefore akin to the diffraction pattern generated by X-ray crystallography, optics or holography. Now all these things again and again we are repeating in many lectures. Do visit our website, or already if you have visited the website, if you have already heard the lecture, you can get understanding of it. With that, we are coming to end of lecture. It was a small topic of K-space, however extremely important. I thank you for giving me your valuable time. Please visit our website for comprehensive and detailed lecture over this topic as well as many other. Thank you, goodbye and take care. See you in next lecture.